Okay, today we're going to talk about inverses and identity of mapping. So before we talk about mappings for inverses and identity, I want to talk about in algebra first, okay? Because we did have inverses and identity for algebra, you guys remember? Especially for multiplication, that's what we're going to talk about. So take a look at this now. So we're going to relate this to algebra. You guys remember what number can I multiply a number so that you get the same number back? Yes. 1. And what's that called? That property, a times 1 equals a. If you, in terms of multiplication, a times, you guys remember this property? Yes. Inverse property? Not quite. Yes. Identity property of multiplication. Very good. And that 1 was the identity. You guys remember this? You guys remember this from like back when you studied algebra? Okay. And you talked about inverse. What is the inverse operation for multiplication? Division, right? So if I have a times what gives you 1. In other words, what can you do to a so that you get 1? You kind of undo what it's doing. So yes, divide by a. But what's another way of writing divide by a in terms of exponential form? Does anybody know? 1 over a, right? So you do a times 1 over a gives you 1. What is 1 over a as an exponential form? A to the, Jason? Negative 1 power, exactly. So so the inverse of a is written as a to the negative 1 power. And there's a reason why, because a to the negative 1 power is nothing more than 1 over a. And what happens when you multiply the number in its inverse? We get 1, right? Does anybody know what property that's called? A times a to the negative 1 power is equal to 1, or a to the negative 1 power times a equals to 1. It's called the inverse property of multiplication. Another name, property of reciprocals. You guys remember? If you multiply the number times its reciprocal, you get 1, and so on. So we know this to be true for algebra. It's very similar things going to work for geometry. I mean mappings as well in geometry. Does that make sense? So let's talk about identity mapping. Look at what identity does to a number. If you multiply a number times identity, you get the same exact number, right? Guess what would happen if you were to apply an identity mapping to a mapping? You're going to get the same. You're going to get the same thing. So for example, here, we're going to use this letter I for identity. If you had a mapping S, if you were to do S of I, you get S back. And if you do I of S, you get the same mapping back. Does that make sense? Can somebody think of a mapping where you're back to... Can somebody think of an identity mapping that we've actually studied? Because we talked about this. What sort of mapping is an identity mapping? Where if you apply this, you're back to where you are. Yeah, Nico?
I don't know, but can you rotate it?
Yes, rotate how many degrees?
360.
360. That's an example of an identity mapping, right? Right? If you were to rotate 360 degrees, right, to some sort of mapping until back to where you are, right? Does that make sense? So that's what identity mapping does. It doesn't. The preimage is same as the image. Does that make sense? So then, what do you think the inverse of this S will be? So we're gonna call it S of negative 1 power, just like how we do it with the number, right? A to the negative 1 power. That's the inverse of A, right? What would S of negative 1 power, the inverse of S? That's how you write inverse of S. What do you think it would do if you were to S of the negative 1 or S of negative 1 of S? If you were to apply S after S inverse or S inverse after S, what do you think you would get? Any idea?
Can you repeat the question?
Yeah, so if I were to do this, what would you end up with? Okay, I want you to discuss with your team. What do you think? What would you get? What do you guys think? I heard some of you say 1, but do we have 1 for mapping? No, there's no 1. Like if you, okay, on the left side, if you multiply a times its inverse, right, you get 1. But for mapping, guess what you get? Instead of 1, you get? Actually, let's think about, let's hold on to this and we'll come back to this. Okay, here, let's do some examples and let's see whether we can answer this. Here we go. So let's talk about the inverse a little bit more before we answer that question. So somebody read this for us. Suppose that there's a pattern underneath. You got a runner running on. Okay, Jordan, thank you.
Suppose that the pattern below continues indefinitely to both the left and the right. Translation T glides to each runner one place to the right. Translation that glides to each runner one place to the left is called the inverse of T, and denoted T to the power of negative 1. Notice that T followed by T to the power of negative 1 keeps all points fixed. So T after T to the power of negative 1, colon, P, arrow, P.
So maps P to P, doesn't it not? So if you were to take the inverse after the transformation T, it maps P to itself, does it not?
Yes.
Why? David, what does that mean? What do they mean by T inverse after T maps P to P? Yeah, why does it map to the same thing? You're right. What does T do? What did they say here? Jocelyn?
T would move the runner like one place to the right.
Yeah, let's just pick one runner, one in the middle right here, okay? Let's pick. What would T do to this runner? Yeah, moves to the right over here, right? Well, you have to imagine that this is going left and right for, infinitely, right? Forever. So the one in the middle, it will go to the right. But what does T inverse do? Go to the left one, so you're back to where you started. You see what the inverse does to T? You understand? So what if I did it twice? So by the way, here, which one do we do first? T inverse or T in this notation? T first, right? Remember the one that's closer to the point? But what if I did T twice? So this person in the middle, this image in the middle will be here and then here, right? And what if I apply the inverse twice again? I'll go back to the same place. Does that make sense? So what T inverse does is it kind of undoes what T, right, did in the beginning. Does that make sense? So this is what you're saying here. T moves it one. Well, if you do T twice, okay, by the way, T moves it once, and if you apply inverse once, you're back to where you are. If you do it twice, you move it, right? If you apply inverse twice again, then you're back to where you are. Does that make sense? Okay, so let's read this part then. The mapping that maps every point to. Go ahead, Jack.
Mapping that maps every point to itself is called the identity transformation I.
Let me move this.
So
Yeah.
words identity and inverse are used for mapping in much the same way that they are used for numbers. In fact, the composite of two mappings is very much like the product of two numbers. For this reason, the composite of S after T is often called the product of S and.
So sometimes they will call it a product. So let's answer that question that we couldn't before. Here we go. So let's go back to this. We said, what would the inverse of then S times S inverse give you? S times S inverse. Hannah? I. How many people agree with Hannah? Anybody have a different answer? Okay, she's right. What does I mean? Identity mapping. It's right. You're back to where you are, right? Does that make sense? What if I did it the other way? S inverse, then S inverse after S. In other words, the inverse after the yes. What would you get? I again. Same thing, right? Does that make sense, guys? So in both cases, you're back to where you started. Let's do some examples, and it'll make more sense. And here's the definition of inverse. Okay, so it may make a little more sense. Here we go. It says, in general, inverse of a transformation T is defined as a transformation such that S after T gives you the identity mapping, right? Which is the mapping that you're back to yourself. Does that make sense? Okay, so when we do an example, it'll make more sense. Right now, it kind of seems sort of not so clear. But let's do some examples. Let me show you. Okay, then you could answer some of the questions here. So take a look at example 1. Let's say we have a transformation that takes x to x plus 5 and y to y minus 4. Okay? What would be the inverse of this transformation? So imagine your pre-image is x comma y, right? And what does this transformation do? It moves it to x plus 5 comma y minus 4. right? We want to find the inverse mapping that will now put you back to x comma y. So inverse mapping is basically, if you have xy, it moves xy to where? I mean, identity mapping is, if you have a point xy, it takes it to where? Xy again. I want it back to where it was. So that's what an inverse, identity mapping is. I keep saying inverse. So what would t to the negative 1, meaning the inverse of this translation be? Go ahead, think with your team. I'll wait. What do you guys think? Okay, so who thinks they know? Jonathan, what did your group come up with? Yeah, so the t inverse will be x minus 5 comma y minus y minus 4? Y plus 4. Would it not, guys? So here's an example. Isn't this what you get? If this transformation takes a point, right? For example, they pick 5, 2. Do I have to use 5, 2?
No.
No. But if it did, not 5, 2. They pick 0, 6. Right? And then 0, 6 becomes 5, 2, right? Now, how do I make 5, 2 go back to where it was before? You do the opposite of, right? What it did. So you subtract 5 and then add 4 to y. Do you guys get the idea?
Yes.
So now you're back to your original point, x comma y, right? In this case, the xy was 0, 6. Do you see? Do you see how my pre-image 0, 6, image of the pre-image 0, 6 became 5, 2? Now, what do I need to do 5, 2 so that I'm back to where I was? Well, you do the opposite operation, right? We added 5 and then subtracted 4 of x and y. You do the opposite of it. Does that make sense?
Yeah.
What about then for a rotation of the x degrees around O? What would the inverse of that be? Everybody go ahead and think as a team. I'll wait. What do you guys think? The second one, rotation around O with x degrees. Okay, what would the inverse operation for that be? All right, Brandon over here, what did your group come up with? For rotation of x degrees around O? Negative x. How many people agree with Brandon's team? Okay, good. You guys are correct. It is, right? Think about this. If you were to rotate here, here's my image, yeah. And if I were to rotate this x degrees, remember when you rotate x degrees, right?
Yeah.
Let's say x is positive, then it's going to go counterclockwise. And then how do I go back? So this is my image, right?
Yeah.
How do I make this image go back to my original place? Well, you go back the same degrees all the way around. Does that make sense? Does this make sense?
Yes, it does.
Do you understand what we mean by inverse mapping? It's whatever you did with that mapping, you undo it. Now I want you to take a look at the C. That's the kind of interesting one. Dilation of D with O and then 2, positive 2. So the K is 2. So dilation around O with K equals to 2. What would the inverse be? This one's kind of interesting. I want you to all try this yourself. Now, may I give you a hint?
Yes.
I would actually draw this and see how this works out, okay? Go ahead and draw, pick a random point, right? And do a dilation of 0, 2, right? And see how you could move that P prime back to original P. Everybody go ahead and try. Oh wait, this is important. This one's kind of interesting. Everybody try. Okay, so let's actually, as I suggested, actually graph this. Okay, so what are we dilating around? Which point?
The origin.
Oh, the origin, right? And let's pick a point, I don't know, 1, 3.
You can.
Which one?
I said 1,
1,
1.
1. Okay, you could pick 1, 1, but then I don't want to have the both order pairs to be, like same, because it may give you some undesired, it may be kind of confusing. 2, 3. 2, 3 is a nice one. Okay, so let's call that P. So where would P prime be if you were to dilate this on the point O with the K equals to 2? First of all, where would P prime be at? Would it be on this ray OP or would it be in the opposite ray? They're the same ray, and so let's draw this. Okay, and then wouldn't it be on this ray somewhere? Can somebody tell me where P prime will go to? Okay, how about who? Okay, Katie, what do you think? 4, 6. How many people agree with Katie? She's correct. You need to go, whatever the distance of OP is, you do it twice, right? So to get to P, you have to go to the right 2, up 3. So do the same right 2, up 3. That will be at twice of distance. There's my P prime. Now, whatever our inverse of d of O2 is, it has to now get p prime back to p. Does that make sense? That's what inverse does. So, did anybody come up with the inverse? Okay, 2 people, 4. Okay, somebody that have Michelle. What did your team come up with?
Dilation around O negative, sorry, 1/2.
1 over 2. Okay, anybody have a different answer? Oh, all of you came with this? Oh, okay. Let's see if this is true. What did you guys get? Oh, okay. Did anybody come up with dilation of around negative half? Or like negative 2, things like that?
No, because of your absolute value.
Yeah, because you know it's not going to be negative. How do I know it's not going to be negative? Okay, think about this. Because it sounds like it should be negative, but we know that it can't be negative. Why not? Why not? How about, here we go. How about Katie? What do you think? Shh. Yeah, if it was negative, right, guys, then it would be on the opposite side of OP or OP prime. What are we looking at right now? We're looking at the P prime, are we not? Because it's now at P prime. So it will be on the opposite ray of P prime, correct? So it will be on this side of this ray, which is not going to get you to where P is. Does that make sense? So we know it has to be positive. You guys understand that? And another thing that's important to understand is you now have to understand we got to look at the P prime as our preimage. Does that make sense? Because P gave us P prime as our image. Now we're trying to figure out another mapping, right? That maps P prime to somewhere. So we're looking at OP prime. You understand? For the inverse, we're looking at OP prime here. Okay. So let's see if this works. Okay. Right. So let's see if this is correct. Let's verify. Well, if it's now we're looking at this P prime, right? We're treating P prime as if that's our preimage, right? So don't worry about this P now. We just want to see whether it goes to P. So if it's D of around O with half, we know it's going to be on this ray again, right? P O P prime. Now we want the distance of this to be what? Half of this O2 P prime, correct? And what would that be? What's the half of distance of OP prime, guys? From the O, it'll be at OP. So that's my P double prime. And so I'm back to where it was. Does that make sense? Does it make sense?
Yes, it does.
So from this, we could actually come up with general formula. What if I have D of O comma K? What would the inverse of any dilation? By the way, O doesn't have to be at the origin, okay? O could be any point, right? But what would the inverse of this be? Because I'm going to put a star on this. Actually, I meant to put a star on this one. So what do you think this will be? Okay, go ahead. For this general case, if it's K, everybody go ahead and think about it. Okay, I'll wait. Everybody go ahead and think of it with your team. Help each other out. So, what did you guys come up with? How about Leah? What did your team come up with?
1 over K.
1 over K. How many people think that that's the inverse? Okay, so David, what did you guys come up with? So one case we think is D of
K to the negative, to the power of negative 1.
K to the power of negative 1. That is 1 over K, isn't it? Okay. So we think it's this, right? Inverse. Let's see whether this is true. Okay. I mean, it is really clear in this example, isn't that right? When K was 2, yes, it did work out this way, didn't it? Yes? Okay, so, well, what if then, let's try for this then. What about D of negative 2? Would it work? So we're saying the inverse of D of negative 2 should be what? If this is true, D of what? Of negative 1 over 2, right? Oh yeah, it was 2. Okay, there you go. So do you think this will be true? Let's verify. So let's use that same point P. And let's see if this puts it back to P double prime. So there's OP. Let's try and D of negative 2. Where would D of negative 2 get this point to be at? On the opposite ray. Okay, uh-oh. So it's going to be on the opposite ray. So I have to go down 3, right? Okay, here, somewhere. Down 3, okay. So it's going to be on this ray, right? So where would P prime be if I were to apply D of negative 2? Because we're looking for the inverse of D of 2. So we got to take P to D of negative 2, right? Where would it go? It goes to P prime, then goes to where? Negative 4, 6, right here. Would it not? Would you agree? Now the question is, will d of around O of negative half, would it take it to p? I would think yes, it will. Oh. How many people say no, it won't? Why not? Why not? Brandon, why wouldn't it take it?
It's still on the opposite ray.
Okay, so now be careful. So that's why a lot of people get confused. We're now looking at p prime, right? OP prime. So what is the opposite ray of OP prime? It'll be on the first quadrant. It'll go this way. Does that make sense? That's where people get kind of confused. People think, oh, wasn't this the opposite ray of the first initial point? Well, yeah, it is true for the first point. But are we looking at the first point, P, or are we looking at P prime now? We're looking at the P prime as our pre-image. Does that make sense? So then the opposite ray, that's right, we do need, and as a matter of fact, we do need to go the opposite ray. Otherwise, if it's not on the opposite ray, it will be on this ray, which will never put you back to the original point. So this is good that it's going to be on the opposite ray. And as you can see, how much of distance do we need of the original ray? This was OP prime, right? We need half of OP prime, which is what? Yeah, which is, you go down 3 to the left 2, so you could go up 3 to the right 2, and we're back to where? The original point. Do you understand? So it turns out this is true. This is the inverse, okay, of d of k, okay? And so it works for negative case also. So that's why I wanted you to understand this part, right? Because a lot of time people think, oh, negative ray, wasn't this the regular ray? Yeah, but that was negative ray of the very original point. We're now looking at OP prime, right? The negative ray of OP prime is on the other side. Is that okay? So this is so then for dilation, that's the inverse. Okay. Any question? So you might want to write that down. The inverse of d of k is going to be d of 1 over k. do of 1 over k. And notice k and 1 over k. What do you notice? They are reciprocals, aren't they? Just like kind of that multiplication we saw, right? The inverse of multiplication, right?
Yeah.
So. May I move on then? Does that make sense? Okay. All right. Good. So let's look at our next example. This is very actually straightforward. What do you think the inverse of this mapping? What is this capital R? What is that, guys? You guys remember? Is it rotation or reflection? It's a reflection. Rotation, remember, it has a cursive R and it's got 2 subscripts. Remember? So this is a reflection of line J, whatever the line J is. Okay. What do you think the inverse of this is? Okay, go ahead, everybody think as a team. This is actually pretty straightforward. All right, let's see. Who have an Krista, what did your team come up with?
Reflection of line J.
Oh, same one?
Oh.
How many people agree with her?
I agree.
Oh.
Okay.
Yes, you affirmed it.
She is correct.
Oh.
Okay. Think about it. I mean, this is sort of obvious. If I show you this picture, it's obvious, right? Look, if I had P right here, and if I were to reflect this on line J, wouldn't it be a P prime? Well, how do I put that back to where it was? We'll do the same thing again, reflect it again on the same line. Does that make sense?
Yeah.
So, Ken, did somebody read this for us? Since, how about Kenneth? Go ahead.
Since R, J,
Reflection on line J.
reflection on line J,
After
R, no, reflection on line J is equal to
identity.
I. The inverse of reflection of line J is reflection of line J itself.
Yep.
In symbols, reflection of line J negative to the negative first power
Mhm.
is equal to the reflection of line J.
Yeah.
Do you see that the inverse of any reflection is that same reflection?
Okay, do you see that?
Yes.
Okay, does that make sense? So whenever we have something to the negative 1 power, we mean the inverse of that. In this case, the inverse of this mapping was itself, the same thing. Does that make sense?
Yes.
So that's kind of interesting. All right, any question? May I move on? Okay, let's do some examples then. Here we go. All right, go ahead and try this example. 1 through 23 odds. Just give me the answers. Just write down the answers. Okay, you don't have to copy down the question. Just try 1 through 27. Write down the answers. These should just take 1 second for each. Really, seriously. So go ahead and try that now. Okay, go ahead. So let's look at the number one. 3 to the negative 1 power. Is that negative 3? Okay, what is it, class? Good. Okay, so remember that's sort of inverse of that 3. What about 3 to the negative 4/5 power? I mean, what? 4 over 5 to negative 1 power? Yeah, because it's really 1 over, right? 4 over 5, which is 5 over 4. What about number 5? It says t moves all points 5 units to the right. If you were to, what does t to the second power mean?
Oh, it means
Joshua?
10 points.
Yes, because it means just you do t twice, right? Right? T to the second power means you do t and then do t. Remember, we kind of equate that with multiplication, sort of, with mapping. So t to the second power means you do t once and then do it again. Okay. All right. What about then t to the -1 power? If it moves 5 units to the left. If t moves 5 units to the right, the inverse of it moves it to the left. So you're back to where you were. Number 9. What do you think? This should be easy. If you were to do t after t inverse, it's the identity. You're back to, right? Exit. The point that you started is back to where it was. Number 11. What will be the rotation? Look, it says rotation R maps all points 120 degrees about G. There's a G right in the middle of this equilateral triangle. So why 120? Because if you were to draw segments from G to each of the vertices, guess what? Each of those angles are 120. 360 divided by 3, right? So where would the R go? If we had A, so they're looking at the A now. Would it go counterclockwise or clockwise? If you do R once, you will go counterclockwise. Remember, you're doing 120 degrees positive. So where would it go, guys? B. Does that make sense? Remember, positive rotation is counterclockwise. What about 13? What does rotation to the third power mean? You do it 3 times, right? So if you do it 3 times, guess what? You're back to yourself. That's the identity mapping, isn't that right? What about number 15? If you're at A, if you're doing 120 degrees as your x, you got to do negative 120 degrees, right? So from A, if you do negative 120 degrees, where would you end up? C, because you're going clockwise. Does that make sense? No, number 17. If you did this, I bet you didn't have to look at this, right? If you do a rotation twice, and then after that, you do rotation twice after you do rotation of -2, right? It's the same place, right? You do it, right? Okay, so does that make sense? Okay. All right, number 19. Did anybody rotate it 100 times or no?
I did.
Okay, that. You shouldn't have to do 100 times. You don't want to do the 100 times. David, what did you do?
Well, you can just. Well, I don't really know how to explain it. I know. It goes around like 99 times and lands on A, and then that last.
That's how you explain it. Why 99 times? Why are you back to A if you did 99 times? Because multiples of 3 would get you the identity mapping, wouldn't it? Right? So if you do it 99 times, that's multiples of 3. You're back to A. You know you're back to A. You just have to go one more. So where do you end up? You end up at B. Does that make sense?
Yes.
Okay. All right. Let's look at number 21. The product of any number t and the identity for multiplication is what? What does identity give you when you multiply? You get back to t, right? What about number 23? What is the inverse of R of a reflection on line L? Yeah, same one. What about for B? Rotation around O with 30 degrees will be negative 30 degrees. Easy enough? What about this translation? X plus 4y. And what about this dilation? It's same as t of, same, t of -1. Why? Yeah, what's reciprocal of -1? -1. Not 1, -1. Does that make sense? Okay, so in this case, it's the same, right? Itself is the inverse. Can you do something like this for your homework? Yeah. Very good.